Hello friends, today we are going to see how to design the culvert deck slab superstructure. Here, culvert to be on the state highway, total width of the bridge slash culvert equals to B equals to L dash, that is 10 meter. That is in the direction of the carriageway. Okay. This section you can see the clear span LC. It is from support to support clear span. So you can see XX section. This section is XX. These are the model properties and different dimensions. So we can assume that thickness of slab in the reasonable way. So if the clear span is 6 meter, let's assume it 500 mm, bar diameter 16, clear curve 40. So we can get these values. The formulas are given here. It could be derived. We can get these values. So this is the easy part. So I will try to explain the live load part, because the dead load, all the formulas are given and it is easy to derive. Generally, the moment and the shear due to the class A tracked vehicle is the governing load for the culvert. So here we have dimension of class A vehicle. The dimensions are given here. The impact factor, it has been adopted from IRC 62017, section 208.3. So it is written in the word. So I have converted it in the value. Up to 5 meter, it is 25%, linearly reducing to 10% for span up to 9 meter. Our span is 6 meter. So the impact factor is 19.75. Now we have to find the position where the moment is maximum. We can see class A loading is almost acting as UDL, and if the UDL is kept at the mid of the span, that is, if the CG of the UDL is at the CG of the span, then it will give the maximum bending moment. That is, X is equal to L by 2. So L, the span 6.4 meter. This one, it is G44. That means LE. So L is equal to LE is equal to 6.4 and width 10 meter. So we can get the ratio 1.56. Now for the simply supported slab, there is one chart. We can get this from different books. So if anybody wants, they can see it here. In our case, for the simply supported, L dash by L is equal to 1.56. So L dash by L 1.56. It is somewhere between this one So for the simply supported, the value should be between this 2.84 and 2.88. So the value adopted here is 2.88. Now this formula can be used. The minimum clearance from the curb. What does this mean? So this is the curb, and the minimum clearance for class A vehicle, it should be 1.2. Okay, like this. The vehicle is assumed to come only up to the distance of 1.2 meter. We do not assume that vehicle will come and touch this one. There is certain clearance. This is 1.2. This value is 1.2, and the net effective width of this portion so here the load disperses like this. There are two cases. In one case, if this curve is short, then it will intersect the curve vertical line, and if this curve is long, then it will not intersect. In that case, we have to find the effective width of this portion. Okay, so this formula I have written here for class A track vehicle, either this one or this one. So we have to add up the minimum of these two values, and if this formula is adopted, then we will get 7.65. So after that we have the formula, and anyone can use this formula to get the value. And maximum bending moment, and due to the live load, is 0.25. Now for the shear force, the value of x is different because the maximum shear force will occur when the load is near the support. In this case, when the load just touches the support, then the maximum shear force is maximum. The shear force is maximum. In this case, x is LP by 2, length of load. So with similar procedure given above, we can get the value of load, and we will get the maximum shear force at the support. Generally, class A vehicle is the governing, so we can just use that vehicle. But here I have also done IRC 70R truck vehicle with a similar procedure, and also IRC class A wheel vehicle with similar procedure. The pedestrian load, it is considered as 500 kg per meter square, and width, this is width of the curve. In this way, the number of footpath, we have two footpaths on the either sides, so total pedestrian load we can get like this, and with this formula we can get the equivalent pedestrian shear and moments. Now the summary of the loads: dead load, slab, wearing. So these are the unfactored loads, live load, and these are the maximum of 2. Pedestrian load, and the shear force, and the factors for our design load. So we have to multiply this load with this factor to get this value. So in this way, for the distribution reinforcement, the transverse moment is 48.93 with this formula. Now let's go for the structural design of slab. So we have these properties of the material. So if the slab is singly reinforced, then we can use this formula. So I have also kept this formula, this formula from IS 456. Now the value of this formula might not be reliable if the grade of concrete is greater than 60 MPa. I will come to that later. So if the reinforcement is single reinforcement, then we can use this formula. So but for this, one thing we have to note is that as for IRC, I have given the formula, but this is a little bit different as per IS 456. Okay. So and to use this formula, the condition of XUL limit by D should be greater than XU by D. Okay. This condition should be fulfilled. And now the moment is 360, but our design moment is 272. It's almost okay. Now if we are using W reinforced section, then another formula given in NXG of IS 456 could be used. Generally, the result of single reinforced section could be used for the W reinforced section. It is considered satisfactory. Generally, we can compare for 16 to the number of bar, the moment resisting capacity is 360. Now, if it is W reinforced, then 366. The effect of compressive reinforcement is generally less in case of RCC. Now this formula, we can get it from IS 112/2020. So this formula can be checked and can be adopted. Design of moment of slab for transverse reinforcement. So this value is this one. Now these are the adapted values for the transverse bar. 12, 7 number can be adopted. You can reduce up to 0.12%. Let's see, 0.12. So this value is also okay. Now shear design. The shear design is as per IS, not as per the IS, but as per IRC 112/2020. It is a little bit different from IS 456. We can see these values and ultimately we will get the capacity of the section. Generally shear bars are not provided in the culvert, so we have to design the section so that it can withstand the shear without the use of shear straps. Now we also have to check the stress. So the stress checking procedure, it is given in IRC 105. So all the formulas are given here. The procedure could be followed. So here we can see the stress is out of limit. Stress in concrete is out of limit. So let's increase the number of reinforcement or the area of reinforcement. First of all, let's link these two values. Now this value, it is taken from this sheet. We have adopted the preliminary dimensions of 16 mm. Now let's change the value to 20 mm. So still now the value is not enough. $25, almost okay. So in this case we can increase the dimension or thickness of the slab. Yeah, now this is okay. So for the double reinforced section we have to do iteration. Now the moment capacity, it is 1070. $959. So the section seems to be very heavy. Let's reduce the number of bars. Seven. Yeah, this is almost okay. 715. Let's do the iteration once again. Now we are getting the reinforcement of 25 mm at the spacing of 142 mm. Now with this formula we can check the values. So everything it is mentioned in ISSP 105 2015. So in this way all the formulas are given. So one thing it should be noted is that in IS 105 this value it is in steel unit, not in the unit of concrete. So this formula can be adopted. So this is bending moment, this value 107 for the crack width check. Unfactored value needs to be taken, D199. This one 107.51. So in this way we can check the crack width. So it should be less than 0.3. Now the deflection calculation, this formula can be adapted. All the formulas are given here. And these values, they are in IRC 112 2020. So it has been mentioned here. And for the long-term deflection check, the formulas are adopted like this. This thing, in this point we have to be careful because the IC, crack moment of inertia, which we have obtained above, that is in the unit of steel. So let's see where is this formula present. So this value should be converted into the unit of concrete. Now the value of phi, it can be obtained from this table. Now the formula of deflection is this one. So M1 and M2 are the moments. As our deck slab is simply supported, they are 0. So we can get the final deflection as this. Now for the drawing, this is the traffic direction and this is the main reinforcement. Let's see how much these values are not correct. So I will change this value. This is taken from another project. So let's see the main reinforcement. We can adopt this value 25 at 135, and this is also okay. 25 at 25 at 125 or 135, it is okay. And at other places, let's see how much we are getting for the transverse reinforcement. 12 at 200, 12 at 200, and other this also we can adopt 12 at 200, 12 at 200, because our design is singly reinforced design. And if we put 12 at 200, let's see in the double reinforced sheet, 12 at 200, so the capacity of this section, it is 734.77, for the single reinforced 715. So only a little bit insignificant difference. So here also we can adapt everything 200. Now this section XX, this one, let's see, the distribution bar, it is above. So first of all, let's check our calculation. This clear cover actually 40 plus, it should be 40 plus this E13 is clear cover, and 40 plus it should be 25, because the clear cover for the distribution bar, it is this 40 plus the bar diameter. So in that case, let's see, this is the main reinforcement, and it is, you can just copy and paste this one, this value, and at other places we can just put 12 at 200. So in this way we can design the deck slab culvert. So if there is any confusion, please let me know in the comment section. I will try to answer as far as possible. And if you like this video, please subscribe and like this video. And if you want this Excel sheet, you can contact me. In my email address. My email address is shibingesar@yahoo.com. Thank you.